GCE Advanced Level Chemistry Practical Series Experiment number 44, Determination of the percentage of acetic acid in vinegar. As you may already know, vinegar contains acetic acid, and in this experiment we are going to determine the acetic acid content in vinegar by titrating vinegar with sodium hydroxide. So, the aim of this experiment is to determine the molarity and the percentage by mass of acetic acid in vinegar by titrating it with sodium hydroxide. To carry out a titration with sodium hydroxide, we first need to know the concentration of sodium hydroxide accurately. So, the very first part of this experiment is going to revolve around standardizing a sodium hydroxide solution with the use of a primary standard such as potassium hydrogen phthalate. Now, let's move on to identifying the chemicals and the equipment we will be using for this experiment. To carry out this experiment, we will be using these chemicals we have here and the equipment we have here. So, let's identify the chemicals we will be using for this experiment. We will be using sodium hydroxide pellets to prepare our sodium hydroxide solution. We will be using potassium hydrogen phthalate. Potassium hydrogen phthalate is a primary standard, so we will be using potassium hydrogen phthalate to standardize the solution of sodium hydroxide that we will be preparing. We have vinegar. We will be using phenolphthalein. This is our indicator for the reaction. We have distilled water. To prepare our solutions, we will be using volumetric flasks. So, we have a 500 milliliter volumetric flask here and 250 milliliter volumetric flask here. We will be using droppers. Apart from that, we will be using pipettes with a pipette filler. So, this pipette is a 25 milliliter pipette we will be using to draw different aliquots or different volumes of the solutions. We will be using spatula, watch glass, and we will be using a digital balance, titration flasks. We have a burette here connected to a retort stand. We have a burette holder as well. Apart from that, we will be placing our titration flask on a white tile so that we can very clearly observe the color changes that take place near the end point of a titration. So, these are all of our equipment and chemicals we will be using for this practical. Let's move on to the very first part of our practical, where we are going to be preparing solutions of sodium hydroxide and our primary standard solution, which is going to be made with potassium hydrogen phthalate. In this first part of our experiment, we are going to be preparing our sodium hydroxide solution. For this experiment, we need 0.2 moles per decimeters cube concentrated sodium hydroxide solution. So, we are going to first measure a relevant mass of sodium hydroxide pellets and dissolve it in water and form our 0.2 moles per decimeters cube concentrated sodium hydroxide solution. But students, as you may know, sodium hydroxide is not a primary standard. When you are measuring sodium hydroxide pellets, it will be very clear to you that sodium hydroxide pellets absorb moisture from the atmosphere, and this will interfere with our mass measurements. It could also finally give us wrong concentration values when you are preparing your sodium hydroxide solution. So after preparing our sodium hydroxide solution, the concentration of sodium hydroxide solution is not going to be exactly 0.2 moles per decimeters cube. To measure the exact concentration of sodium hydroxide, we can use a primary standard such as sodium potassium phthalate. To measure the exact concentration of sodium hydroxide, we can use a primary standard such as potassium hydrogen phthalate. So when we are starting off this part of our experiment, we are going to first prepare a sodium hydroxide solution, and after that we are going to prepare a solution of potassium hydrogen phthalate, which is going to act as our primary standard. So let's first move on to measuring the relevant mass of sodium hydroxide. We need to prepare a 0.2 moles per decimeters cube concentrated sodium hydroxide solution. We are going to be using a 500 milliliter volumetric flask to prepare our sodium hydroxide solution, and we do know the molecular weight or molecular mass of sodium hydroxide. Based on this volume and the molecular mass of sodium hydroxide, we have calculated that we need to weigh exactly 4 grams of sodium hydroxide. At home, you can use the molecular mass and the volume of this volumetric flask and carry out the calculations yourself and observe how we obtain this 4 grams value for the mass of sodium hydroxide. We can now move on to measuring the sodium hydroxide that we need to prepare the sodium hydroxide solution. In order to do that, we will be using a digital balance, and let's turn on our digital balance here. After turning on our digital balance, we can place a watch glass, and we can use the tare function and make our digital balance read 0, and we can take our sodium hydroxide. In this bottle we have sodium hydroxide pellets. With the use of a spatula, we are going to be adding 4 grams of sodium hydroxide onto our watch glass here. Students, we have measured exactly 4.01 grams, and after measuring our 4 grams of sodium hydroxide, now we can add this sodium hydroxide to our volumetric flask. Let's go ahead and do that. Students, one thing that you will observe when you are conducting this experiment in your school labs is that when you are measuring sodium hydroxide, the sodium hydroxide pellets that you obtain from the bottle are going to have a matte, dull appearance. However, when you take it to your watch glass, when you are carrying out the measuring process, or when you are trying to measure the mass of the sodium hydroxide, you will see the sodium hydroxide pellets, they start to glisten. This is because they will start to absorb water from the atmosphere, and they will dissolve in this atmospheric water, and a layer of moisture will be covering the sodium hydroxide pellets. If you observe here, now some of these sodium hydroxide pellets are starting to glisten, and as I move them around, you can see some of them leave a trail of liquid. Some of them leave a trail of liquid because they have absorbed water from the surrounding and has formed a layer of moisture around them. So this is why sodium hydroxide is not going to be a good primary standard. A primary standard should have a few characteristics. One of them is being non-hygroscopic, meaning not absorbing water from the surrounding. Sodium hydroxide certainly does absorb water from surrounding. Apart from that, sodium hydroxide will also react with the carbon dioxide in the atmosphere, which makes it not a very suitable substance for a primary standard. So after observing this, we can now move on to adding this sodium hydroxide to our volumetric flask here. For this, we will be using a wash bottle as well. We will first place a funnel on top of our volumetric flask. When you place the funnel on the volumetric flask, you do not want the funnel to sit right on the lip of the volumetric flask. You wouldn't want the funnel to sit right on the lip of the volumetric flask, creating a flush seal. When you have a seal created like this, what will happen is when you are pouring water in, that the air that is getting displaced due to the volume of water that is coming in has to exit through this hole. So when that is happening, you will notice the water that you pour in starts to splash all over the place. So to avoid that from happening, you can lift the funnel a little bit and then you can add your water, so that as the water is delivered into the volumetric flask with the help of the funnel, the air that is getting displaced has enough room to escape the volumetric flask from the mouth of the volumetric flask. Let's take our sodium hydroxide pellets. We'll lift both the funnel and our wash glass with one hand like this, or if you want to have a clearer view, I'll try to do it with my other hand, with my right hand. So you can hold it like this and you can add your water with the use of a wash bottle. You have to make sure that you wash the entire surface of the watch glass. After washing the top surface, you can flip it around and wash the bottom surface a little bit as well. After washing the watch glass like that, you can continue to add water to the funnel, washing the internal walls of the funnel really well and dissolving any sodium hydroxide pellets that are found on the funnel. After doing so, you can even wash the tip of the funnel with a little bit of water and keep the funnel aside. Now students, we have added our sodium hydroxide into our volumetric flask. You can swirl the volumetric flask to dissolve the sodium hydroxide that is in this volumetric flask. Dissolving of sodium hydroxide in water is going to be a little exothermic, so you will feel that the solution inside this volumetric flask has a little bit of a higher temperature. You will continue to stir it until all of the sodium hydroxide is dissolved well. Now students, we will continuously stir it for a while, and when you are stirring it, please make sure that you don't hold it all the way from the top and stir it like this, due to the neck of this volumetric flask being very narrow. When you are holding it from over here and exerting a force, there is a likelihood of damaging the neck of the volumetric flask. It may even result in breaking the equipment. So when you're holding the volumetric flask and you're stirring it, you can either hold it from the bottom or close to the narrow end over here, and then you can stir it like this, right? Do not hold it all the way from the top and stir it like this. That is wrong. So continuously stir it until all of the sodium hydroxide is dissolved, and then you can move on to adding a little bit more water. We have distilled water here. After that, you have observed that we have dissolved all of the sodium hydroxide, you can add water up to this calibration mark that we see over here. We have distilled water in our beaker here. We'll be adding water all the way up to our calibration mark. We'll be adding more water. Now we have added water quite close to the narrow end of our volumetric flask. From this point onwards, you can use a dropper or a wash bottle to add water close to our calibration mark. So let's use a wash bottle to add a little bit more water carefully. When we are reaching towards the calibration mark, it is always advisable to use a dropper to add the last few drops of water so that you don't go above the calibration mark when you're adding water. So let's bring our volumetric flask to our eye level so that we can very clearly see the calibration mark at our eye level, and we can proceed to add water few drops at a time. Now we are only a few drops away from the correct volume, and with just one more drop we have prepared a solution of sodium hydroxide approximately 0.2 moles per decimeter cube concentration. So the reason why I said the concentration of sodium hydroxide over here is approximately 0.2 moles per decimeter cube concentration is because sodium hydroxide is not a primary standard. When we are weighing the sodium hydroxide, we might have absorbed some water into the sodium hydroxide, and that might have shown in our final reading as well, which could lead to the concentration of sodium hydroxide not being exactly 0.2 moles per decimeter cube concentration. Now students, after filling up the volumetric flask all the way up to our calibration mark, we can proceed to close the lid of our volumetric flask and we can start to mix it further. So when you are mixing it further, please hold it from the bottom and place your finger on the stopper, and then you can turn it upside down a couple of times to make sure the solution is mixed really well to produce a homogeneous solution of sodium hydroxide. After preparing our sodium hydroxide solution, we can label it and keep it aside. For the time being, we can leave it aside and move on to preparing our primary standard, which is potassium hydrogen thalate. Now students, let's discuss why we have to use potassium hydrogen thalate as our primary standard here. Sodium hydroxide, as I mentioned earlier, when you are weighing a specific mass of sodium hydroxide, we are not very sure whether we have actually obtained the mass of sodium hydroxide that we needed to prepare that solution. This is because sodium hydroxide is hygroscopic and it will absorb water from air. Apart from that, it could also react with the carbon dioxide in the atmosphere. So therefore, in the solution that we prepare, the amount of sodium hydroxide might not be what we assume it to be, because sodium hydroxide might react with carbon dioxide, or when you're measuring the mass of sodium hydroxide, we might measure it incorrectly due to sodium hydroxide being hygroscopic. However, when it comes to a primary standard is a very stable compound which is not going to be undergoing any decomposition easily. So a primary standard is a stable compound and something that can be obtained with a high level of purity, and it is going to be non-hygroscopic, meaning it will not absorb moisture from the atmosphere, and it will have high solubility in water, and it is supposed to be non-toxic and should have a high molecular weight or high molecular mass to avoid the errors that are normally introduced through measuring a substance. So when you're measuring a substance with the use of a digital balance or analytical balance, if that equipment has a small error, the way in which it affects your mass readings will be less if you are measuring a larger amount of substance. So having a high molecular weight or high molecular mass is going to be beneficial. So when it comes to our potassium hydrogen thalate, it has all of these characteristics. It is a stable compound. It can be obtained with a high level of purity. The potassium hydrogen thalate that we have over here has an assay of 99.5%. So we have obtained it with a really high percentage of purity. It is non-hygroscopic. It is very soluble in water. It is non-toxic, and it has a high molecular weight. The hydrogen potassium thalate has a high molecular mass or molar mass. So the molar mass of this substance is going to be 204.22 grams per mole, or if you are talking about molecular mass, it is going to be 204.22. So this makes hydrogen potassium thalate a really good primary standard, and we can measure it very accurately and prepare a solution with a known concentration. So when you prepare a solution with potassium hydrogen thalate, the resultant solution is going to have a concentration that is known to us. The sodium hydroxide solution that we prepared earlier, although we wanted it to have a concentration of 0.2 moles per decimeters cube, we wouldn't know whether we have actually prepared a solution with that concentration. We have errors. However, when it comes to potassium hydrogen thalate, when we prepare a solution using potassium hydrogen thalate, we can be certain of the concentration of the solution that we have prepared. So therefore, potassium hydrogen thalate is a good primary standard. We are going to use this weak acid potassium hydrogen thalate to standardize the sodium hydroxide solution that we have prepared here. Then we will be moving on to using this standardized sodium hydroxide solution to carry out a titration between acetic acid and sodium hydroxide. Now let's move on to preparing our standard solution using potassium hydrogen thalate. Now we are going to be moving on to preparing our standard solution using potassium hydrogen thalate. We have our potassium hydrogen thalate here. Students, on this bottle containing potassium hydrogen thalate, on the label we have a lot of valuable information such as its molecular mass and its assay. So if you take a look at the assay values here, you will note that it has an assay of 99.5%. So using these values, you will be able to calculate the exact mass of potassium hydrogen thalate that you will be needing to prepare a 0.2 moles per decimeters cube concentrated solution of potassium hydrogen thalate. So we are going to be preparing a solution of 0.2 moles per decimeters cube concentrated potassium hydrogen thalate. In order to prepare this solution, we have calculated that we need to measure exactly 10.26 grams of potassium hydrogen thalate. So we have our digital balance here. At home also, you will be able to calculate the mass of potassium hydrogen thalate that is required to make a 0.2 moles per decimeter cube concentrated solution by using the information that you see here on the label. You can see the molecular weight given here, 204.22, and we can see other information such as the assay of this potassium hydrogen thalate that we have here in the lab. So you can use this information to measure the mass of potassium hydrogen thalate you should be taking to prepare a sample of 0.2 moles per decimeter cube concentrated solution. So now we'll use our digital balance here. We'll turn it on, and we can place our watch glass here, and we'll use the tab function to get the digital balance reading to a 0, and then we can proceed to measure 10.26 grams of potassium hydrogen thalate. Students, as you can see here, we have measured 10.26 grams of potassium hydrogen thalate. We can now proceed to adding this potassium hydrogen thalate to our volumetric flask and then preparing our standard solution. Let's first close our potassium hydrogen thalate container here, and then we can take our funnel and our volumetric flask. After placing our funnel, we can proceed to transfer this potassium hydrogen thalate very carefully into our volumetric flask. We slowly start adding water with the help of a wash bottle. After washing the wash glass thoroughly, you can turn it upside down, or we can turn it around and wash the bottom bit of the watch glass as well to remove any residue of potassium hydrogen thalate that still clings on to the watch glass. Afterwards, you can proceed to wash the internal wall of our funnel as well. After doing so, after washing the tip of the funnel, we can remove the funnel from the setup, and we can now start stirring or swirling this solution to dissolve the potassium hydrogen thalate that is present inside our volumetric flask. We will mix it really well. Now, when potassium hydrogen thalate is dissolving in water, you can observe the solution cools down, indicating dissolving of potassium hydrogen thalate in water is slightly endothermic. So after dissolving it a little bit, you can proceed to add a little bit more water. before we add water all the way up to the calibration mark, you have to make sure that all of the solid that we have taken into our volumetric flask is fully dissolved. You do not add water all the way up to the calibration mark before dissolving the solid. After dissolving the solid, then you will proceed to add water all the way up to the calibration mark. You will not add water when the solid is still undissolved. Keep that in mind, students. It's very important. Now, students, we have added quite a bit of water and we have dissolved all of the solid that was present inside the volumetric flask. We can now proceed to add water all the way up to the calibration mark here. In order to do that, we can lift the volumetric flask all the way up to our eye level and then proceed to add water with the help of a wash bottle. After we have added water quite close to our calibration mark, we can shift to adding water with the help of a dropper. The final few drops of water can be added very carefully with the help of a dropper. This could use one more drop. Now, students, we have added water all the way up to our calibration mark here. You will be able to observe it clearly that the bottom of the meniscus aligns perfectly with our calibration mark. So this means we have added the right amount of water to our volumetric flask. We can now place the stopper and turn this volumetric flask upside down a couple of times to make sure the solution that we have made is a homogeneous solution by mixing the contents inside the volumetric flask really well by turning it upside down a couple of times. Now we have prepared our 0.2 moles per decimeters cube concentrated potassium hydrogen phthalate. So the solution that we have in front of us is the potassium hydrogen phthalate solution that has a concentration of 0.2 moles per decimeters cube. Let's move on to standardizing our sodium hydroxide solution that we prepared earlier using our primary standard that we have prepared here. Now we are going to be standardizing our sodium hydroxide solution we prepared earlier. We have our sodium hydroxide taken to a beaker and we have our potassium hydrogen phthalate with 0.2 moles per decimeters cube concentration. Again, we have taken that into a beaker as well. Students, when you are taking these solutions that we have prepared with a high level of accuracy into beakers or into any other glassware, please note that the glassware is completely dry. If it is somewhat wet, please proceed to wash the glassware with the solution you have prepared first before including the solution in the glassware. So before taking this solution into this glassware, if there are any water droplets in the container, proceed to wash it with a little bit of the solution first and discard the solution. After discarding the solution, you can take a new sample of this solution into the beaker. Otherwise, the water droplets present on the walls of your beaker might dilute the solution that we have prepared. So when it comes to handling any glassware, you have to wash it with distilled water first and then with the solution that you have prepared. Especially when it comes to this type of titrations where we are trying to be as accurate as we can, we are going to always wash each of these glassware twice, once with distilled water and the second time around with our solution that we are planning on taking into our glassware. So we will be using this pipette to accurately measure 25 cubic centimeters of potassium hydrogen phthalate, and then we'll be taking it into this quite dry titration flask. So we are going to first wash this with distilled water. In fact, this is already washed with distilled water. We are going to be washing it a second time with our potassium hydrogen phthalate. So let's take a small amount of potassium hydrogen phthalate, wash our pipette with the solution, and then proceed to withdraw an aliquot of potassium hydrogen phthalate using this pipette. So to draw the solution onto our pipette, we have a pipette filler. You can fix the pipette filler onto the pipette and then take a small volume of potassium hydrogen phthalate into our pipette. And you can remove the pipette filler after that, and then we can proceed to wash our pipette by rotating it and coating the entire interior surface with our potassium hydrogen phthalate solution. As you can see, the entire interior wall of our pipette is now washed with our potassium hydrogen phthalate sample, and then we can discard it to a different container. Then we can move on to filling this pipette with our potassium hydrogen phthalate, and we can proceed to measure exactly 25 milliliters of potassium hydrogen phthalate using this pipette, and then we can transfer that volume to our titration flask here. To do that, we'll first fix our pipette filler like this, and by pressing the upper valve here, you can release the air. After releasing the air using this valve, we can draw our solution into the pipette by placing the tip of the pipette inside the beaker, and as you can see, the solution will be drawn into our pipette. And students, please note that there is a calibration mark over here, so you have to only fill it all the way up to that point. If you draw more liquid passing that point, you can drop it so that the bottom of the meniscus aligns perfectly well with the calibration mark. We can bring it to eye level to fill the pipette accurately. Now students, the meniscus aligns perfectly with our calibrated line here. Now we are going to transfer this volume to a titration flask. And when you're transferring this volume to a titration flask, make sure the tip of the pipette touches the interior wall of the titration flask. And then you will have the volume of the solution to run through the pipette onto the interior wall of the titration flask and get collected inside our titration flask here. Keep in mind students, there will be a small drop of the solution remaining at the tip. No need to push it outside of this pipette, or you don't need to blow it out of the pipette. The pipette is calibrated in such a way that it accounts for this drop of liquid to remain at the tip of the pipette. So you do not have to blow it out. So please understand, if you blow it out into the solution will contain an additional droplet of the solution. Now after taking our potassium hydrogen phthalate into the titration flask, we can add a drop of phenolphthalein as our indicator. We have our phenolphthalein indicator here. We are going to add few drops of phenolphthalein indicator into this titration flask, and now we have our titration flask and the contents in it prepared for our titration. Now we can proceed to taking our sodium hydroxide into our burette here. We have a burette here which is already washed with distilled water. We can proceed to wash it with sodium hydroxide, and then we can fill it all the way to the top and proceed to carry out our titration. So before starting to wash your burette, make sure the burette is tightly closed. Then we can proceed to add small amount of sodium hydroxide to our burette here. After adding a small amount of sodium hydroxide to the burette, we can wash the interior walls of the burette by placing the burette somewhat horizontal, and then we can rotate the burette, making sure the entire interior surface of the burette is coated well with the sodium hydroxide solution. We can make sure that the entire interior wall of the burette is washed with this sodium hydroxide solution. Afterwards, you can discard it, discard the excess sodium hydroxide by opening the stopcock of the burette that we have here. After washing the burette, please make sure to close this stopcock tightly. If you don't tightly close this stopcock that we have over here, it is going to be a bit of a problem when you're trying to fill sodium hydroxide into our burette. So when you're trying to fill sodium hydroxide, you will see as you fill sodium hydroxide will run through the pipette burette tip that you have over here. So now let's proceed to fill the burette. Again, we are going to make sure that it is completely tightly closed, and then we can take a funnel, place it on our burette like so, and we'll have to bring this entire setup to our eye level first, because we are not supposed to take any chemical above our eye level or above our heads and start pouring into the funnel. So that is not something that we recommend that you do. So whenever you are filling a burette, you have to bring the burette down to your eye level first, or you have to bring the funnel below your eye level so that you can easily pour your sodium hydroxide solution into your burette. So in order to do that, you can actually grab a stool and place the burette setup on the stool, and then start filling the burette. So let's proceed to do that. Now let's place this on a stool. Now students, as you can see, you don't have to lift any chemical above your head in order to pour something into this burette. So we can easily take our sodium hydroxide, which is going to be our titrant in this experiment, because we do not know the concentration of sodium hydroxide that accurately. So we will take sodium hydroxide, and as we fill sodium hydroxide into the burette, we are going to lift the funnel a little bit so that it leaves enough room for air to escape. We will fill it all the way up to the top. As students, as you may have already observed, I have filled sodium hydroxide above the zero line all the way to the top. This is to make sure that we have enough of sodium hydroxide solution to make sure that the tip of the burette is also properly filled with sodium hydroxide. As you know, when we washed this burette with sodium hydroxide, we made sure the tip of the burette remained empty, and when you are filling the sodium hydroxide into our burette, we have to make sure that we take a little bit of an excess amount of sodium hydroxide, so that when you are trying to fill the tip area of the burette, you have enough of a volume to drive out the air bubbles that are actually found in the tip of the burette. So let's take the burette here. And we can observe the tip of the burette here. And when you open this top cork, you can see that the air bubbles are getting removed from this tip. You can very clearly see the air bubble is getting pushed out of this tip. And there is another air bubble over here near the stop cork. To remove that air bubble as well, we would need to open this stop cork a bit faster and rush the sodium hydroxide solution through that area so that the air bubble gets pushed out quite fast. So let's open it really fast and then close it. Now we can be sure that the air bubble that we had over here is completely removed, as well as the air bubbles that we had over here, or the air gap that we had on the tip, is also completely removed. Now students, after making sure the tip area doesn't have any air bubbles trapped in it, we can move on to bringing down the meniscus all the way to the zero line. Now before I do that, I want you to ask yourselves, why is it very important to remove the air bubbles or air that is trapped in the tip of the burette? Air is compressible. So therefore, when air compresses and expands, the volume that we read here might be incorrect. So you might get to incorrect volumes of sodium hydroxides that are measured through this burette if you have air bubble trapped in the burette or in the tip of the burette. Now we can again bring it down to our stool and bring the meniscus down to the zero line and align it with the zero line. Now students, the bottom of the meniscus and the zero line are aligned perfectly. So when they are aligned perfectly like this, we can say we have successfully filled our burette, and then we can move on to our titration. We have successfully filled our burette that we have in front of us, and we have our titration flask here. Inside our titration flask, we have potassium hydrogen phthalate, and the concentration of potassium hydrogen phthalate is known to us. It is 0.2 moles per decimeters cube. Now students, we can move on to titrating this potassium hydrogen phthalate solution with the sodium hydroxide solution that we filled into our burette. I hope you know how to operate a burette by now. You have to make sure that you don't mishandle the burette. You have to correctly operate it in the following manner. And as you pour the sodium hydroxide into the titration flask, you have to make sure that you swirl the titration flask around like so, so that whatever the contents that are introduced into our titration flask gets mixed really well. So let's start our titration. We are going to add sodium hydroxide drop by drop. You can see as sodium hydroxide is added drop by drop, there is a slight pink coloration that appears, but when you mix the solution really well, that pink color disappears. The pink coloration that you see over here is due to the presence of phenolphthalein indicator. Currently, this titration flask contains only potassium hydrogen phthalate, which is a weak acid. In acidic medium, phenolphthalein will not have a color, or phenolphthalein will be colorless. However, when you add sodium hydroxide, the acid content that we have here in the titration flask will gradually decrease due to the acid reacting with the sodium hydroxide we introduce into the titration flask. So at one point, we will completely react all of the acid that we have here with the sodium hydroxide. After all of the acid is completely reacted with the sodium hydroxide, the next incoming drop of sodium hydroxide will turn this solution into a pink color, because in a basic medium, phenolphthalein will display a pink color. So we are going to be carrying out this titration until we observe a pink color. Let's proceed to do that. You can see as sodium hydroxide is added, the color of the solution immediately changes to a pink color, but as we mix the solution well, the pink color disappears. We don't have a persistent pink color. The point at which we obtain a persistent pink color is the point that we consider as the end point of this titration. You can see the sodium hydroxide drops when they come into contact with the solution. Now the pink color that is formed is a bit more persistent than it was before, indicating that there aren't many acid molecules remaining in the medium. So now you can start adding sodium hydroxide drop by drop to get to the correct endpoint. We are almost at the endpoint. We can see now it takes a while and a lot of stirring to get the pink color to disappear. When we add a sodium hydroxide drop, you can see now this pink color doesn't disappear that easily, but if you mix it really well, it disappears. That means there are still acid molecules that will react with the sodium hydroxide. But there are only a very few. That's why the pink color is going to be quite persistent. Now we can very clearly see the pink color persisting without getting disappeared. So this indicates that we have reached our end point. This indicates we have reached our end point, and at the end point we need to read the burette reading. The burette reading is 26.3 milliliters or 26.3 cubic centimeters is the burette reading of our first titration. So students, for the very first titration, the burette reading was 26.3 cubic centimeters. So I want you to keep in mind, students, when it comes to doing titrations, we normally repeat the same titration 3 times to obtain concordant results, to make sure that each titration or the titration readings that we have received as close as possible to the accurate value. So after obtaining the first titration reading, we'll be moving on to the second and the third titrations. So let's move on to the second titration. Now we move on to our second titration. We'll get a clean, dry titration flask, and we have the pipette that we have washed earlier. So we are going to use this pipette to measure 25 milliliters of our potassium hydrogen phthalate solution. After measuring exactly 25 milliliters of potassium hydrogen phthalate, we will be releasing this volume into our titration flask. Now we are releasing the potassium hydrogen phthalate solution into our titration flask. After we release, or after we transfer the potassium hydrogen phthalate into our titration flask, we will be adding our indicator, phenolphthalein. We are going to add 3 drops of phenolphthalein into the titration flask we have here. After that, we can mix the solution really well. After mixing the solution well, we can move on to conduct our titration. We have a burette here that is freshly filled with the sodium hydroxide solution that we prepared earlier. So the burette is filled all the way up to the 0 line. We can place the titration flask under the burette like we did in the previous instances, and we can proceed to titrate the potassium hydrogen phthalate like we did in the titration 1. Now observe, students, when I add a few drops of potassium hydrogen phthalate, almost instantly the pink color that appeared disappears. You can see upon addition of a single drop or few drops, the pink color that you observe will disappear quite fast. However, you will notice towards the end of the titration, this pink color will take some time to disappear, and with the last drop, you will observe that will produce a persistent pink color in the solution. So since we know the very first titration gave us a burette reading of 26.3 milliliters, we are going to add sodium hydroxide all the way up to around 20 or 21 cubic centimeters without problem. However, after that, we are going to take caution, we are going to be careful and add sodium hydroxide drop by drop to our titration flask. We can proceed to add sodium hydroxide a little faster, all the way up to around 20 cubic centimeters. As we know, the end point is around 25 or 26. Now students, I have added 23.5 milliliters or 23.5 cubic centimeters of sodium hydroxide. You can now observe when a few drops of sodium hydroxide is added, how long it takes for that color to disappear. This indicates that the amount of acid molecules in the solution has gone down compared to the initial concentration. The acid concentration here has gone down. Why? Because we added sodium hydroxide and the acid reacted with the sodium hydroxide. Potassium hydrogen phthalate, which is an acid, reacted with sodium hydroxide, and therefore the acid concentration in this titration flask right at this moment is lower than when it initially started. So we can see the pink color persisting a bit longer. But when you mix it, you can see it disappear. We can continue to add sodium hydroxide drop by drop. and eventually when we observe a persistent pink color, we have come to our endpoint, or we have obtained our endpoint. We have obtained our endpoint here. That is a very slight pink color that you can observe very clearly here, indicating that we have obtained a persistent pink color. This persistent pink color is observed because the medium is now basic, because all of the potassium hydrogen phthalate acid molecules have reacted and you don't have any acid molecules in this solution anymore. So therefore, we can observe a persistent pink color. So at this point, the burette reading is exactly 26.4. So the burette reading is exactly 26.4. So students, as you observed, when it comes to the second titration burette reading, it was 26.4 cubic centimeters, and the first one was 26.3 cubic centimeters. So these two readings are concordant, as the difference is within 0.2 of a cubic centimeter. So therefore, we have obtained two concordant burette readings. We can now move on to our final titration and finish standardizing our sodium hydroxide solution. Like we did in the previous two titrations, we have our titration flask and we have our potassium hydrogen phthalate solution over here, and we are going to use our pipette to withdraw 25 cubic centimeters of our potassium hydrogen phthalate. Now students, when you're measuring, you have to always make sure that you bring your pipette to your eye level. Right, we have measured exactly 25 cubic centimeters of potassium hydrogen phthalate. Now we can transfer it into our titration flask. After transferring a potassium hydrogen phthalate into the titration flask, we can proceed to add 3 drops of phenolphthalein into our titration flask, as we did in our previous titrations. Now we can mix the contents in the titration flask and we can place it under our burette like so. And students, we have again another burette that is filled all the way top to the 0 mark. We didn't fill the burette on camera. We have the burette already filled all the way up to the 0 line. So we are going to now start the titration as we did in the previous two instances. As we know, the endpoint is obtained close to 26 cubic centimeters. We can proceed to add sodium hydroxide a little bit more faster. While adding sodium hydroxide, make sure to stir your titration flask or the contents in the titration flask really well. And you will observe now gradually the pink coloration that you observe in the solution is becoming more and more persistent. I have added 23 cubic centimeters of sodium hydroxide now. We can now proceed to add sodium hydroxide a bit more slowly. Now with a few drops now, you will observe a color change. So we have to be very careful at this point. It is my intuition or my feeling that just one drop will be sufficient to bring about a color change now. As you can see, the color changed slightly to a pink color, and you can obtain the reading at this time. So as you can see, students, although we observed a pink color, on standing it disappeared. That means there is still a little bit of potassium hydrogen phthalate that was present in the medium. We can add one more drop to observe the pink color clearly. You can see with just one more drop we got to a very clear pink color. So now we can take the reading. Reading is 26.4 cubic centimeters. Now students, with the third titration we observed the burette reading was 26.4 cubic centimeters. So the very first titration gave us a burette reading of 26.3. Second and the third titrations gave us a burette reading of 26.4. So all of these readings are concordant. Now you can collect this data and carry out a calculation to find the exact concentration of the sodium hydroxide solution we prepared earlier in this experiment. So now through this titration, now you have the information to calculate the actual concentration of the sodium hydroxide solution that we prepared earlier in this experiment. Now students, we are going to move on to the second part of this experiment, that is titrating the acetic acid in vinegar with the use of the sodium hydroxide solution we have prepared here. Now students, we are going to use a sample of store-bought vinegar and find out the acetic acid concentration in the store-bought vinegar. In order to do that, we would need sodium hydroxide to titrate the vinegar, and we have found out the concentration of sodium hydroxide solution we prepared earlier in the part 1 of this experiment. We have standardized the sodium hydroxide solution. So now we know the exact concentration of the sodium hydroxide that we have here. We have filled the sodium hydroxide into the burette all the way up to 0 line, and we are going to take 5 cubic centimeters of vinegar into a titration flask, and we are going to dilute this vinegar with the use of 10 cubic centimeters of water. So why do we have to dilute the vinegar? The vinegar, depending on what type of store-bought vinegar it is, might have different colors. Depending on the manufacturing process, the color of the vinegar might vary, and this color might interfere with our titration, because at the end of the titration, we will get a color change. In this particular experiment, we are going to be using phenolphthalein, and in the titration flask we are going to have vinegar and water mixture, so it is an acidic solution. And when we add phenolphthalein, there will be no color, or phenolphthalein will be colorless in acidic medium. But when we are reaching the end point, or when the end point is reached, we are going to observe this colorless solution is going to turn into a pink color. So if the vinegar already has a very strong color, you might not clearly see this color change. So to dilute the color that is observed in vinegar, we are going to be using 10 cubic centimeters of water. And to measure the vinegar very accurately, we are going to be using a volumetric pipette, and we are going to measure exactly 5 cubic centimeters of vinegar. and transfer that amount into our titration flask here, and then we can proceed to add 10 cubic centimeters of water. Now, when you're measuring the vinegar, you have to make sure that you measure it with a very precise measuring equipment, because we need to make sure the amount of vinegar that we take into the titration flask is a constant. When you are adding water, you can add water with the use of a measuring cylinder as well. So let's first take our store-bought vinegar that we have here and take small amount of this vinegar into the beaker we have here. As you can observe, students, this vinegar has a very strong yellow-brown color. So if this color persists, it's going to be difficult for us to observe the color change that is going to take place at the end point of our titration. So that is why we are going to only withdraw 5 cubic centimeters of vinegar into the titration flask and dilute it using 10 cubic centimeters of water, as twice as much as the volume of vinegar that we have taken will be used to dilute the vinegar, so that the color that you observe here will be diluted. So first of all, let's take our pipette. We are going to wash the pipette with vinegar first. So we are going to insert the pipette in vinegar and draw a small volume of vinegar into our pipette, and then we will take the pipette out and wash the pipette with vinegar, and then we can discard the excess vinegar into a different container. Now we have washed our pipette. After washing the pipette, we can proceed to take 5 cubic centimeters of vinegar. So this volumetric pipette can be filled all the way up to 0. So if you fill it all the way up, then you have to release, or we have to transfer only 5 cubic centimeters of vinegar into the titration flask. But to make it easier for us to transfer the right amount of vinegar, we are going to release 5 cubic centimeters of vinegar into the stock solution first, and then only retain 5 more cubic centimeters of vinegar in the volumetric flask, in the volumetric pipette, so that it will be easier for us to transfer exactly 5 cubic centimeters of vinegar into our titration flask. So let's release 5 cubic centimeters of vinegar back again into our stock solution. Now we have taken exactly 5 cubic centimeters of vinegar into this volumetric pipette, and we will be transferring it to our titration flask. Now we have transferred it to our titration flask. We can keep the pipette aside, and then we can proceed to add 10 cubic centimeters of water. We can use a measuring cylinder. And now we have measured 10 cubic centimeters of water. We have measured 10 cubic centimeters of water here, and then we are going to be transferring that into our titration flask. Now students, you can observe the color of the solution that we have inside our titration flask. It is not as strong as the color that we observe here. It is not as strong as the color we observe here in the stock solution of vinegar. Now, after we have diluted the vinegar, we can now start titrating. But before we start titrating, we have to add few drops of phenolphthalein indicator to this vinegar solution. So we have our phenolphthalein indicator. Let's add 3 drops. Let's add 3 drops of phenolphthalein indicator to our vinegar solution, and we have mixed it really well by now. After mixing it really well, we can proceed to start our titration. In the first part of our experiment, I did mention how titration is carried out, and we have already filled the burette here as well. So only thing that is left for us to do is continue our titration. We'll start the titration, and as we add sodium hydroxide, just like in the previous titration, you can see when a drop of sodium hydroxide is added, the color of the solution changes really fast into a pink color, but again it changes to colorless due to the acid or the acetic acid present in the medium. Just like in our previous titrations, you can observe as sodium hydroxide enters the solution, that area of the solution turns pink. This is because sodium hydroxide or phenolphthalein, when comes into contact with OH- ion or phenolphthalein in high pH values, will display a pink color. However, this medium that we have over here is acidic. When sodium hydroxide enters this medium, sodium hydroxide will react with the acetic acid in vinegar and will get used up. However, after all of the acetic acid is completely reacted, the next incoming drop of sodium hydroxide is going to convert this acidic solution into an alkaline or basic solution. At that point, you will observe phenolphthalein changing its color from colorless to pink. So that will be our endpoint. Let's carefully add sodium hydroxide to this solution to obtain our endpoint. You can see as soon as sodium hydroxide is added, there is going to be a pink color, but immediately this pink color will disappear due to medium being quite acidic. That indicates that we have enough and more acid in the medium still. As we add more and more sodium hydroxide, there will come a time that the pink coloration will persist for a little while longer before disappearing. When you are adding sodium hydroxide, if the pink coloration that you observe is not going to disappear immediately, this indicates that the acid concentration of the solution at that point is very low. And after all of the acid is reacted, you will observe a persistent pink color. Right now, the pink color that we observe disappears as soon as I mix the solution, indicating we still have enough acid. When we are closer to the endpoint, you will observe the pink color will persist little while longer before disappearing. So at that point, you can start to add sodium hydroxide a bit more carefully to obtain a more accurate endpoint. Now, students, observe when we add a few drops of sodium hydroxide, the pink color doesn't disappear straight away, indicating that the acetic acid concentration now in vinegar is very low because sodium hydroxide has reacted with it. So when we add a few more drops, we might observe a very clear color change. Now, we can observe that we have obtained a very persistent pink color solution, indicating that we have achieved our end point. So, we have obtained our end point, and the amount of sodium hydroxide or the volume of sodium hydroxide that we have spent on obtaining this endpoint is 21.4 cubic centimeters of sodium hydroxide was spent in order to obtain this endpoint that we have here. So, this is our first titration. We'll have to repeat this same experiment or same titration 2 more times to obtain a better idea about the accuracy of this reading. So, let's move on to our second and third titrations. In the second titration, we will follow the same exact steps. We will be taking our volumetric pipette and we'll be drawing 5 cubic centimeters of vinegar into the pipette, and we'll transfer 5 cubic centimeters of vinegar to a titration flask that we have here, and then finally we'll add 10 milliliters of water to this titration flask. So, let's proceed to do that. We have our volumetric pipette. We'll draw 5 cubic centimeters of vinegar. We have taken exactly 5 cubic centimeters of vinegar into this pipette, and then we can transfer it to our titration flask. After transferring it to the titration flask, we can proceed to add, we can take our measuring cylinder and measure 10 cubic centimeters of water. Right, we have measured exactly 10 cubic centimeters of water here, and we will be transferring that into our titration flask. We will mix the solution well, and then we will take our phenolphthalein indicator, and like we did in our previous experiments, we will be adding 3 drops of phenolphthalein indicator to this solution. After adding the phenolphthalein indicator, we can mix it really well, and we can place it under our burette. Now, students, we have a burette that is freshly filled with sodium hydroxide solution we prepared earlier. It is filled all the way up to our 0 line here on the burette. So, all that is left for us to do is now start our titration. We know we obtained our very first burette rating at 21.4 when we were carrying out the first titration. So, we can be somewhat certain that when it comes to second titration also, we will obtain our reading around 21 cubic centimeters or maybe close to 20 cubic centimeters. So, we have the option of adding close to 20 cubic centimeters of sodium hydroxide somewhat fast into our titration flask. But we have to keep in mind, as we add the sodium hydroxide to our vinegar solution we have here, you have to be very careful, because if you do not stir the solution, you might be misled to believe that you have already obtained an endpoint, because as sodium hydroxide enters the solution will slightly turn to a pink color, but when you mix it, this pink color will disappear. So therefore, students, whenever you are carrying out a titration, it is crucial to keep stirring or keep swirling the titration flask so that the contents in the titration flask mix really well. So let's proceed to our titration here. Since we know the burette reading from the first titration, we can add around 15 to 20 cubic centimeters of sodium hydroxide a bit faster this time around, because we do know that the burette reading from the first titration was 21.4. Now students, I have added 19 cubic centimeters of sodium hydroxide. Now you will observe when I add a few drops of sodium hydroxide, the pink color stays or persists for a while. This is not your end point. When you mix it, you can see the pink color disappears. So that's what I mentioned earlier. When you are adding sodium hydroxide to this titration flask, it is crucial to always stir it or mix it well. Otherwise, you might be mistaken and you might mistakenly believe that you have obtained the end point when you have not. So it is very important to keep stirring or mixing the contents in the titration flask. So we are quite close to the end point now. We can start adding sodium hydroxide dropwise. We can see the solution is still clear. It is not pink. We are getting very close to the end point here. So with another few drops, we might observe the end point or the color change. Now students, we can see a persistent pink color. We will swirl it around or mix the contents really well to observe whether we can see a change in the color. But no, we can very clearly see a very visible persistent pink color. We can very clearly see a visible persistent pink color, and that reading was obtained when we have added 21.3 cubic centimeters of sodium hydroxide to our titration flask. So the burette reading is 21.3 cubic centimeters. So now we have conducted our second titration as well, and we have obtained our second burette reading. Now we can move on to our third titration. Students, we have observed the first and second titrations, and we have gotten readings that are concordant with one another. First titration reading was 21.4, and then the second titration reading was 21.3 cubic centimeters. Both of these values are within the difference of 0.2 of a cubic centimeter. So therefore, these values are concordant. All that is left for us to do is our third titration. We'll follow the same exact steps that we followed for the first and the second titration and complete this set of titrations. We have our volumetric pipette here. We'll use this to measure 5 cubic centimeters of vinegar. We have measured exactly 5 cubic centimeters of vinegar. Now we can transfer this into our volumetric flask. Now we are going to transfer this into our titration flask, not the volumetric flask. This is the titration flask. So after transferring it into our titration flask, we will be adding 10 cubic centimeters of water to the same titration flask. We'll be measuring exactly 10 cubic centimeters of water, and after measuring exactly 10 cubic centimeters of water, we'll be transferring this amount of water into our titration flask. Now, just a reminder, students, why do we add water to our vinegar and form a bit of a dilute vinegar solution? What is the purpose of this particular part of our experiment? As you already know, vinegar, depending on what brand of vinegar that you might have bought or what type of manufacturing process they have followed, will have a different color. It is not going to be a very clear solution. Especially the vinegar that we have over here is somewhat a yellow-brown color. So the color of the vinegar is going to interfere with our titrations. That is why we will be diluting the vinegar with the use of 10 cubic centimeters of water. After diluting the vinegar, we'll move on to adding 3 drops of phenolphthalein. We have added 3 drops of phenolphthalein to the contents or vinegar solution that we have here in the titration flask, and then we will mix it really well. After mixing it really well, we can place it under a burette and we can now start our titration. In the first 2 titrations, we learned that the amount of sodium hydroxide that is going to be used in order to obtain a very clear color change in the solution was 21.3 and 21.4. So roughly around 21.3 cubic centimeters of sodium hydroxide should be added to this titration. Therefore, since we know the end point, we can proceed to add sodium hydroxide all the way up to around 19 or 20 cubic centimeters without any hesitation, as we do know that the end point is going to be obtained close to 24.3 or 24.1. So just to be on the safe side, we usually start adding sodium hydroxide drop by drop after we have reached a volume of around 19 cubic centimeters, just to make sure that we do not pass the end point. So we can proceed to add sodium hydroxide a bit faster this time around, but keep in mind, students, you have to keep stirring or keep swirling the titration flask so that the contents are mixed really well. Now I have added 15 cubic centimeters of sodium hydroxide. Now, students, I have added 19 cubic centimeters of sodium hydroxide. Still no color change. So from this point onwards, we are going to be adding sodium hydroxide dropwise, more slowly, so that we can control the amount of sodium hydroxide that is added to the titration flask. And you can observe whether there is a color change very clearly, and you have more control over stopping the flow when you are adding sodium hydroxide drop by drop. Now we can see the pink color persists quite a while, meaning we are close to the end point. As you can see, students, we have obtained our end point. So students, you can see this pink color is persistent. It does not go away no matter how many times I keep swirling it around. When I mix it also, the pink color of the solution does not disappear, indicating that we have obtained our endpoint. The pink color is persistent because the solution is now basic. Earlier on, in the presence of acetic acid, the solution would have been acidic, but all the acetic acid has now reacted with sodium hydroxide. So therefore, after adding one more drop, the entire solution has turned to a basic solution, and in a basic solution the phenolphthalein indicator would change its color to a pink color. So that is why you observe this very clear pink color which is persistent over here in our solution. So at this point the reading is exactly 21.4. The reading is exactly 21.4. So the very first titration reading was 21.4. Second titration gave us a reading of 21.3, and the third titration gave us a reading of 21.4, indicating all of these burette readings that we have obtained through these three titrations are concordant. So therefore, you can use all three of these burette readings for your calculations to figure out the concentration or the percentage of acetic acid in vinegar. So students, in this experiment, we learned that sodium hydroxide cannot be used as a primary standard. So what did we do? We used a primary standard to standardize sodium hydroxide. Sodium hydroxide was standardized by a solution of potassium hydrogen phthalate. After standardizing the sodium hydroxide solution, we have to calculate and find out the concentration or the actual concentration of sodium hydroxide solution. After calculating the actual sodium hydroxide concentration, we can use that solution to titrate the acetic acid in vinegar. So now we have titrated the acetic acid in a vinegar sample, and using the burette readings that we obtained here and the concentration of sodium hydroxide that we have calculated earlier, we can calculate the number of moles of acetic acid that was present in 5 cubic centimeters of vinegar. Based on these values, you can calculate the concentration of acetic acid in vinegar and also the percentage or mass percentage of acetic acid in vinegar.